Good morning. I am Joost Wendt from the University of Utah, and it is my pleasant function to introduce Mikko Hooper for today's plenary lecture. And Mikko is rector, which is the president of Åbo Academy in Finland, and is professor in inorganic chemistry. And I have known Mikko for several decades. I have special admiration for his work because as an inorganic chemist, Mikko made it his function to integrate fundamental chemistry with practical and real industrial processes. And he was very successful in doing that, and especially in the biomass treatment or biomass use area, and also in the pulp and paper industry. In fact, Mikko is well known as an after-dinner speaker for in the pulp and paper industry dinners that occur every few years. He served as director of the National Combustion Research Program, or LAKI, in Finland in the 90s, and made that an outstanding success. It was one of the programs that one looks to as a model for multifaceted combustion research programs. He was a superintendent of research and director and president of the International Flame Research Foundation, which is an organization that is dear to my own heart, and he did a wonderful job there too. He has published many, many, many papers, and I won't list the number of where it was. And he's now also the chairman of the board of the Åbo Academy of Process Chemistry Center, a center of excellence in research. So with that, I have to say that in addition, Mikko is a world-class tennis player, I've been told, and a very accomplished jazz pianist. But I guess we'll have to wait for those performances at a later date. For now, I'd like you to welcome Professor Hooper.
Thank you very much, Joost, for your very kind introduction. Good morning, everybody. I want to start by thanking the Combustion Institute for this great opportunity to come and talk to you, and particularly the program chairs Assad Masri and Peter Glarbury. Thank you very much for inviting me. It is a pleasure, and it's an honor. I hope I can meet the expectations, at least to some degree. I also want to acknowledge my co-authors for this presentation, Oskar Karlström, Emil Vainio. They are my younger postdoc researchers who did a lot of help when we put together this presentation. I will speak about biomass combustion, and my main focus will be biomass combustion in larger units. It is heavily increasing in Europe and in Northern Europe, and there is a lot of interesting technology around it. The large-scale combustion of biomass can take place as co-firing together with other fuels, can be also co-firing with coal, but then it can also be done in a separate large-scale biomass units. And here are two examples of such units. Fluidized beds. The upper one is a circulating fluidized bed by Foster Wheeler, and the lower one is a bubbling fluidized bed, another type of technology. And both of these are quite interesting when using biomass in large scale. For those of you who are not familiar with this kind of technology, here is, you get an idea of the size. This is the guy you may be seeing here. They are very big units. One important trend at the moment is the increased interest into lower grade biomasses. Wood as such, which was the starting to all this technology, in fact is a relatively easy fuel in many ways. But when the interest goes to lower grade biomasses, many interesting things start happening on one hand. On the other hand, they are quite interesting fuels because they are cheap in price and they are easily available. So people have now started more and more talking about opportunity fuels rather than harmful wastes. However, now we approach my topic of today. These poorer quality fuels give a lot of challenges to design and operation. They are not straightforward to be used. And a lot of that has to do with chemistry, chemical details. The devils are in chemical details, definitely in this business. And there is a lot of space for fundamental research which can support this development of technologies and the use of low-grade biomasses. So I will touch some part of that also. Biomass is defined in different ways. This is a good one. Organic matter derived from living or recently living organism. The graph which is used for coal, where we have hydrogen-oxygen plot, hydrogen to carbon ratio, oxygen to carbon ratio, shows quite nicely how biomasses relate to coals. So in this kind of graph, anthracite coals are down here, of course, very low hydrogen, very low oxygen. The younger coals will place themselves here, brown coals, lignites further ahead. Then comes an interesting group of fuels called peat. They are just in between before coming to the biomasses. So in a way, biomasses are very, very young coals, but from combustion point of view, they are much more than that. And there are many other aspects. In this kind of a graph, the heating value goes in this direction. And I have another picture showing also the same relationship. Here you see starting from anthracite, the volatiles content goes steeply up, and in fact for most wood qualities or biomass qualities we speak about 80+% volatiles and 20% fixed carbon. The lower heating value in the same way goes down, so they have a low heating value, but on the other hand, as I mentioned, some of them are quite available and inexpensive. Very importantly, they have very different ashes as compared to coal. The whole ash chemistry is different. For instance, the ash indexes being used in coal have absolutely no relevance when it's about biomasses. Here is an example of one modern large-scale unit using biomass. It's a circulating fluidized bed in Jakobstad, Finland. Here is also the guy, so it's a huge unit, 550 megawatts, and it has the possibility to burn very different fuels. Extremely interesting concept, but very demanding. You cannot burn all of these fuels from 0 to 100%. You have to know very well which combinations are possible. One additional point here is to show that also here where the main fuel used to be bark or still is bark or wood, but there is an increasing interest to start using also something we call forest residue. Forest residue is the material that stays in the forest after the paper guys have taken the logs. And this green material consists of branches and needles and so on. There is a big interest. There is also new technology to more efficiently collect that material and bring the material in the same trucks that are used for logs for this fuel. And then it can be burnt. However, if we take a look at the composition of wood, you see here immediately that things become more demanding when using green parts of the wood. Look at the potassium content. In wood, it is very, very low. In bark, higher. But when we go to twigs, the small branches, it's even higher. And needles. And if somebody would be interested in just analyzing the annual growth, the potassium content is extremely high. So the more green material is there in the mix, the higher is the amount of ash-forming elements, and it concerns almost all of the elements. These are the most important ash-forming elements in biomasses: alkali metals, phosphorus, sulfur, and chlorine. And their chemistry, there is similar chemistry in coal firing also, but the key here is that this is the main chemistry. In coal firing, it's the minor chemistry, and the main chemistry is on the silicate, aluminum silicate side. Here is a summary of ash-forming matter in different biomass fuels, and you see here that wood has a very low ash content, and the champion here is rice husk, where the ash content is, or ash-forming matter is 9%. This is percentage elements, so if we take it as an oxide, then it's silicon oxide. This is almost pure silicon oxide. It's 20%. So rice husk is a very interesting biomass fuel also. I will come back to the composition of this just in a moment. Now, we collected with Emil and Oskar here some locations in a big unit where chemical aspects play an important role when designing the unit or when operating the unit. And you can see that there are many locations, many aspects where chemistry comes in, where chemical knowledge is needed to be able to design or to be able to operate the unit. Fluidized bed, very special feature is the bed sintering. Fluidized sand bed is sensitive. If it starts changing composition, it may start forming larger particles, and it may defluidize. Very, very difficult and common problem when using biomasses. Nitrogen oxide chemistry requires good knowledge of air staging or vice versa. Carbon conversion, something about fuel reactivity. Additives are used. I don't go deeper into them. Steam data, steam temperature is really the key parameter where biomass combustion has big problems. I will come back to that. Low temperature corrosion, of course, and emissions and so on. So this I like to show to our students and try to motivate them to use and join us to do chemistry, because it is badly needed here. I have chosen here a few examples of the more fundamental work and try to connect them to these problems. And they deal with these 4 areas. And I start with some words about biomass fuel reactivity. Biomass particles have the same stages of combustion as coal. There is a drying stage, Normally there is more water in biomasses than in coal. The devolatilization stage, the char and the ash. The devolatilization is more important. 80% of the mass will disappear there. Also, the char properties are not only is the char smaller, but the properties are also different. And I have a few examples here of char. Now, these are test results which we did by using the data from the International Flame Research Foundation database, which were produced in this drop tube furnace. Here are mass loss, or in fact char carbon conversion for anthracite on one hand, bituminous coal, and biomass. The residence time 1.5 seconds. This is just the char, so it's not the complete fuel. And you see that the anthracite char very little reacts, to a small degree, while biomass already can burn the whole char in this very short time. This is the same size, same mass of char, but the reactivity of the char is very, very higher for biomass. That higher reactivity has to do with the ash ingredients in biomass. So now we come back to particularly the alkali metals and potassium. And quite recently we wanted to learn a little more about which factors affect the char reactivity, and we took biomasses and produced chars with different content of potassium, just to see how the potassium influences. And here we have a biomass which we had completely washed before producing the char. So the potassium content was 0. And then we added potassium, even in different forms, to the fuel, produced the char, and measured the char reactivity by TGA. And here you see the char oxidation rate % per minute. Now, this is not in air, this is in carbon dioxide, where the same reactivity is also easy to detect. And you see, in a funny way, almost linear correlation. We didn't add enough potassium to see it leveling out later. Definitely it will do that. This is just an interesting thing to learn, that it's so sensitive to the potassium content. The reactivity summary: very high volatile content, extremely reactive char due to catalytic metals. Char oxidation by CO2 and H2O is also so fast that even in ordinary combustion, those reactions need to be taken into account besides the direct reaction with oxygen. So that is, we have seen it when modeling the particle burning, that the gasification reactions need to be taken into account. Otherwise, we don't get it correct. This has a very important technical consequence. It is that since the char is so reactive, that explains why we can burn biomasses using the bubbling fluidized bed technology, where all the char combustion takes place here in the bottom of the boiler, instead of going to the circulating bed where the char particles have a long residence time in the circulation. This is needed for coal because of the char unreactivity. But here we can burn. This is much more simple. This is a less expensive solution. In fact, the bed itself here in the bubbling bed is slightly reducing, so there is not very much oxygen there. So the char conversion mostly takes place by CO2 and water vapor gasification. Some words about nitrogen chemistry. It's not very well studied before. You would expect it to be similar to the coal, and partly it is, but partly there are nice surprises. The nitrogen content in different wood qualities you see here, and we are in the range of 0.1 to 1%, slightly lower than for coals, but it's still there. If we burn individual particles, like here, in a laboratory, we can see nitrogen oxide formed. First the volatile nitrogen oxide, and then later here you see the char nitrogen. Even if the char amount is small, it still also produces nitrogen oxides. This is similar to coals, but of course the ratios between these two is very dependent on the quality, on fuel quality. We were curious about this shape of the char nitrogen oxide production. Why is there hardly no at the beginning of the char oxidation, and then there is the maximum production is just before the char is burnt out? It was maybe not practically so important, but it was a fascinating question to ask, so we studied it a little more. And in fact, we could repeat it. It was very reproducible. Here you see similar curves, three different temperatures. And in fact, the higher the temperature, the more clear was this upgoing trend. These are the carbon dioxide releases during the same tests. The explanation here is that during char burning, we produce NO, which is a heterogeneous process. Part of the produced NO, of course, is diffusing away from the particle, but part of it can diffuse into the particle, and that is the key to this phenomenon. This ingoing NO will be reduced to N2 because of the active char. And here, again, the specific reactivity of the biomass chars gives the explanation. This you don't see with ordinary coals, but here the reaction goes this way. We can model it, we can produce a standard model, and if we take into account the diffusion of NO and oxygen into the particle, we can create a model which reproduces nicely this phenomenon. But what was more interesting, we did tests in a large-scale unit. This is the unit. It's a fluidized bed with a big freeboard. You see almost 40 meters, and we wanted to try to sample inside such a furnace and see how nitrogen oxide is formed. This was the topic. This particular unit burns mostly bark, but it also has additional fuels. In our test, which I'm going to show, we were burning only bark. And you see the nitrogen content in bark is about 0.4. And I will show our equipment because this was quite a challenging work. Now I have great respect to measurements in the laboratory with sensitive equipment, but this is a different game when the equipment grows to 50 meters by 10 meters. We used large sampling probes, pipes, and we put them into different locations in a systematic way. The probe was very special design. In fact, it had 4 pipes inside each other. And the sample, the gas sample, was taken, or it was continuous sampling. It was not just, the gas was sampled in the inner pipe and fed to the analyzers. The inner pipe, the outermost part here is a ceramic piece which allows a heavy, quick dilution of the sample and cooling to make sure there is no additional reactions in the pipes. But we should not cool too far because then we get condensation of material. So we needed to heat the rest of the pipe. So it was cooling, quick cooling and heating. And this one worked very well, finally. Here you show it an example where we located it inside such a huge furnace. Here are the fuel feeding chutes, and the probe was 4 meters long, so we reached almost 2 meters into the furnace from different sides. And this kind of a signal we received. And you see that we could detect clearly ammonia. This is now from that particular position in the lower furnace. So we found a lot of ammonia, smaller amounts of NO and hydrogen cyanide. And then we had to clean the pipe quite often and then get a new signal. Here, this is 1.8 meters into the furnace. Then we pulled it a little further back, so it was only 0.8 meters in, and we get another signal. And this we did in many locations in that unit. Here you see the locations. And there were a lot of interesting data. Here you see the lower furnace, nitrogen species, and then we had them all over here. And finally, the flue gas nitrogen oxides, 92 ppm. There were a couple of interesting details here which we focused. One was that we did find relatively large amounts of hydrogen cyanide, which we didn't expect, because in laboratory tests or in tunnel furnaces, you don't detect so much hydrogen cyanide for biomasses. It's almost all ammonia. But here, obviously, we have a chemistry in the lower furnace where some hydrogen cyanide also is produced. But the more interesting surprise was that there was an extremely heavy reduction of the fixed nitrogen along the furnace. So in the lower furnace, we had almost all fuel nitrogen converted to fixed nitrogen. But then when we went up and made measurements in different locations, here are those points are collected, the ammonia, hydrogen cyanide, NO contents went steeply down here, and then they stayed a while unchanged, and then they continued going down, and finally were only about 10% of what was original. This is a very good reduction. On the other hand, these boilers were not built for NOx reduction, so this was something that came by themselves, and we were quite curious how to explain this. Here we thought that we may try to use some modeling, because here the special feature with these units is that they have here, their air distribution is quite new type. It's very heavy jets. These air jets here are about 7-8 meters with a velocity of 60-70 meters when they come in. So they form a very, very heavy horizontal jet. And we thought that maybe these heavy jets have something to do with this effect. And we created a model where we simplified the furnace in the way that we assumed that most of the chemistry takes place in the jets. And this is the approach we used. We first calculated the jet size and entrainment approximated by computational fluid dynamics. And then we used, for chemistry, we used detailed chemistry, but the reactor assumption here was that we have a gradual entrainment of flue gas continuously according to the entrainment laws using this sweetening reactor, so smooth feeding of continuous feeding. This way we can put the complete chemistry in and see what happens. And here is the result of that calculation. This, of course, assumes that we have a very efficient mixing radially, which is not the case, but that was the assumption here. Let's look at the results. This is the complete jet. This is 7.5 meters. It's a very long jet. And early, it's almost pure air, of course, and the temperature is low. But the temperature keeps increasing when more and more hot gas is mixed in. Yeah, I forgot to explain that we used as a feeding material the measured primary combustion zone composition. So we wanted to see what happens to that gas when it's going into the jets. And here the temperature increases until we come to somewhere 800. And in this period, 2.5 meter, chemistry doesn't play a role yet. It's frozen, it's too cold. But then at somewhere here, the chemistry starts playing a role, and we see that the entrained ammonia suddenly disappears. Some NO is formed, and then they both disappear. So there is a steep decrease in the total fixed nitrogen until we have used all oxygen in that jet, and the final part, no chemistry anymore, only entrainment of neutral flue gases. This is quite remarkable. My students started calling this DeNOx region, but it's definitely not DeNOx in the meaning that we would add something, but it has similar chemistry, ammonia and nitrogen oxide in that jet form conditions where the DeNOx chemistry becomes very active. Then the same happens in the tertiary air jet. So we feed this gas composition in there, and we have a similar history. Cool period until we start again getting some similar reaction. NO, TF, total fixed nitrogen goes down, but we are already in a quite low concentration here. And interestingly, the final NO, or total fixed nitrogen, we get with this modeling is about 100 degrees, and you remember that was 90 or something that we measured out. So obviously, this technology to have these heavy jets, which were aimed to improve the combustion, not to do DeNOx, were efficient in this way also. Some summaries of this: almost complete initial conversion of fuel nitrogen to fixed nitrogen gases in a lower furnace, but then 90% reduction. And we think that this is a special feature of this new air feeding technology. For circulating fluidized beds, the nitrogen chemistry is very different, but I can not go into that. There, the char reactions start playing a role. Corrosion, very important part of biomasses. And in fact, that's the biggest challenge in the technology development for these boilers. It's caused by chlorides on tube surfaces. That's quite clear. There everybody is agreeing, but then I will tell you later that we don't agree about all the details of this corrosion. This is the reason why the steam data, parameters are much lower in even the most modern power plants with this type. 500, 520 degrees is a very high number if we burn biomass fuels. While, as you know, in coal boilers we can go beyond 600, and the materials issue is still not there. And a simple rule of thumb is that every 10 degrees we dare to heat superheater steam higher, gives 2% more power in the turbine. You can check if that is a correct rule of thumb, but in that range, which means that there is a big interest into improving this situation. And our boiler manufacturing colleagues, which we work together with, are extremely concerned about finding solutions to improve the efficiency, the power production efficiency. Now we come back to chlorine and the ashes, and you see here, this is chlorine, and particularly these kinds of biomasses the agricultural annual plants have high amounts, but also other biomasses have small amounts of chloride. And I will show that it's sufficient with relatively small amounts to cause these problems. But before that, I want to go a little into the mechanism of chloride corrosion because it is interesting. This is a nice concept given by Nielsen et al., and it's quite often referred to. Here would be the steel surface, iron, chromium, and here are the flue gases. And the key is this deposit containing chlorides. So far, everybody agrees. Now, in this concept, the idea is that the chloride is activated in the deposit by reactions caused by sulfur dioxide from the flue gases. And the chloride is released as Cl2 gas. And that Cl2, chlorine gas, will react on the surface forming volatile iron and chromium chloride. This has been a difficult mechanism. Sometimes we have results which agree with this, but I will show you some results which do not agree. And you will see them here. We do our laboratories, when we do corrosion, we do it quite simple. We have a sample plate of different steels. We put some salt on top of them, treat them in a furnace-controlled atmosphere. 1 week has shown to be a long enough time to get a good signal. And then we cut the piece and do microscopy on that. And here I show one quite big study we did a while ago where we compared 6 different steels for chloride-induced corrosion. 6 steels, starting with carbon steel, with most of it iron, and then going nicely, they are commercial steels, but systematically going to more and more advanced. These are austenitic stainless steels, and these are high alloy nickel materials. It's good to know here that if this costs 1, this will cost about 40. So they are extremely expensive ones, these, because of the quality of the steel and the nickel content. Now, then we did a full series of temperatures 450 to 600 with all these steels. And in fact, our students did all these tests, but under these conditions, when we used only as base material alkali sulfate, no chloride yet, we got no corrosion for most of the steels except the steel number 1, which is the low quality. And this is not caused by the salt. This is just any oxidation of that material at high temperatures. But you could see that if we have no chlorides, we could easily have material temperatures up to 600 with all these materials without any problems. That would be very welcome because then we would be able to go higher temperatures, steam temperatures. However, when we start mixing chlorides, small amounts of chlorides into this system, this is the one I showed to you. We put 0.3% chloride. We did it by putting sodium chloride or potassium chloride into this sulfate, melted it in advance, and cooled it and crushed it. So it was very homogeneously mixed, the chloride. And you see that now these materials already start showing heavy corrosion. These are high numbers. These are micrometers per week. And this is already visible by eye on that short time. And when we have 1.3% chloride, even the most expensive materials started showing clear corrosion at 525, explaining how this is really the obstacle to going to higher steam temperatures. But the interesting part here was these tests were made with no presence of sulfur dioxide, which was the key in this concept. So we are quite sure that this SO2 is not needed, only that we have this deposit and we have high temperature, the things start happening. So we need some other mechanisms to trigger the corrosion. I don't go deeper into this, but the key is that when we do this kind of microscopy, we can see that after a weak exposure, the potassium is still on the surface, but it is no longer together with chlorine. So there is a split of potassium chloride, but this is not because of the sulfur dioxide. It's just straight on the surface. And we know from many tests it's an interesting formation of potassium chromate, the chromium layer on the surface. And that chromate formation has not really been so well reported before. Now it is a great, interesting thing. And which conditions does the chromate form? It doesn't form a long while. It's just an intermediate which breaks the surface. Small amounts of alkali chlorides are sufficient for severe corrosion at 500 plus C. This is one conclusion. Alkali chlorides are corrosive also in absence of SO2. This alkali chromate formation has become an interesting thing. There is work going on. We try to understand a little better why, how that happens. And it's almost amazing because if you read the literature, the chloride corrosion has been there 30, 40 years, and we still keep arguing about the mechanistic things. But that makes life fascinating also. How do the manufacturing companies react to this? Today, this is the largest ever boiler running only biomass. It's 447 megawatt. The one I showed earlier was mixture of biomass and other fuels. This is only biomass. Here you see the critical temperature is 535, so they have really extended it up to the maximum, but didn't dare to go further. And how do they do this? Because they also use agrobiomass, which is the more difficult one, containing chloride. One solution they have, which is interesting, this is Foster Wheeler in Poland. In a circulating fluidized bed, this is the furnace. The bed material is circulated back, and there is a feeding system of that back to the furnace. That feeding system is also a small bubbling fluidized bed, and they put heat exchanger, the hottest superheater, in there, and could increase the steam temperature somewhat by the contact with the hot sand without the contact of the flue gases and the chloride. This is one way of showing how things advanced anyway. Now, a few words still about ash deposits. Corrosion is one aspect, but then the whole fouling issue is also another one. And one detail we were interested in, that we know that when we sample ash deposits, either with probes or from the boiler, we see that the deposits are not homogeneous. They look different on the tube surface as compared to flue gas. And it's quite obvious because there is a temperature gradient across the deposit. There was a lot of discussion of how does this temperature gradient influence the deposit with time. There were speculations, maybe something happens. And we were wondering if we can study that in the laboratory. Now, it's not easy to create a steep temperature gradient in the laboratory. We have if you calculate, you can show that if this is the steam side, this is the tube wall deposit. So we can have, and this is flue gas, so if we have 1,000 degrees here, 500 here, steel will be, of course, about 5, 20, 30. But we can have a gradient of temperature of several hundred degrees, 200, 300, 400 degrees in the deposit. So the material which is in the deposit has an interesting environment. Finally, recently we were able to produce such a gradient also in the laboratory this is not a very clear picture, but the idea is we have a cooled pipe where inside temperature was 500 degrees, for instance, and then we can put our deposit sample here. But we have to cover the rest of the tube for heat transfer reasons. And then if we have only that part open and we have a hot furnace around, we can create something very similar. And we can have a gradient inside that deposit. And it was interesting. If we put a layer of salt on that gradient condition and let it be there one day, this is what we saw. Here are this is the salt deposit. This is the cooled steel. Here has been the hot environment. So instead of having a homogeneous particles which look like something like this, we can see that the outer side is almost molten, semi-molten, and this is a mixture of, we used here as a model substance is sodium sulfate, sodium chloride, which is a good model because we know that it's melting behavior very well. So this is logical. Here we have 500 degrees, and then somewhere here this system starts melting at 730. So somewhere here we have had a temperature of 730. But if we take a closer look into this, we start seeing that also the type of the particles have changed. The particles didn't look like this when we put them in. So now they have this white layer on top. And if we take one more close-up, we can see that, yes, each particle has received this white layer of material, and also the lower part looks different. Now, the center of this particle shows how they looked before, at the beginning, original salt mix. So we have the sodium sulfate gray matrix and sodium chloride crystals in that matrix. They were prepared by melting and cooling, so that's how it looks. But with 24 hours in this gradient, temperature gradient, the sodium chloride started vaporizing and condensing to different particles, some kind of a vapor transport, which took place quite quickly. And now today we think that we understand that quite well. So if the cold is down, hot is up, this is the way it goes. So simply sodium chloride starts vaporizing and is removed from the lower parts of the particles, and then it hits the next particle. And the interesting thing is that the driving force here is extremely small temperature difference. These are small particles, 100 micrometers, but it's sufficient to transport material. And the consequence of this is that this chloride will partly go all the way to the steel surface, depending on the temperature conditions, and can enrich high amounts of this, even small amounts of chloride. So this is something we want to study more. We have been able to model this phenomenon by a two-dimensional vaporization condensation model, and we can get some theoretical curves which fit quite well to the layer thickness. We can measure the potassium layer thickness as function of time. This is a new area. We call it gradient chemistry in inorganic chemistry in temperature gradients. It can be important in other applications as well. Deposits change with time due to temperature gradients. Volatile chlorides migrate towards the cooled tube surfaces, and it may have an effect on corrosion properties of the deposit. Now, these were examples of fundamental work which support the continuous development. Of course, one small piece of fundamental work never gives the final solution to the design of the units, but we've been very happy with our collaboration with these companies, that they have worked with us many years, so gradually the information we have been able to produce and the communication we have with them has led to that we have been able to do a lot of stuff which has shown to be directly useful. How will the future look? It's clear that biomass today is mostly used by combustion. In fact, the bioenergy from biomass is 95% still based on combustion. But we have heard many good presentations here in this conference as well about other optional ways of using the biomass to create other energy carriers. And this will, of course, be a trend which will continue. And here we are quite sure that there's a lot of space to research, because whichever technology we start using here will be very sensitive to the biomass feedstock quality, and we are back in the impurities, chloride, nitrogen, and so on. This is one highly interesting project going on. There are, I think, 2 or 3 plans in Scandinavia to go for biodiesel production combined with ordinary pulp and paper mill. It has the advantage that the pulp and paper mill has a huge logistics system for biomasses, and we have these biomass residues which are not used in the plant, which could be used elsewhere. And the idea here is to have a parallel line where we have a oxygen-blown gasifier, gas cleaning, Fischer-Tropsch synthesis. Would be highly interesting. A lot of technical challenges there, a lot of interesting work to be done. But that is one option. I would like to finish by also stressing that it's good to do research work, which is not directly related to problems also in our area. And I want to show you one interesting piece of work by one of our co-workers, Andrei Pranovic. He's a wood specialist, and he was interested in analyzing one annual ring from the wood cross section. And he had a technology to take that one annual ring area and microtome it into slices. So not only did he analyze the ring in average, but he wanted to know how that ring consists as function of time. And this is what he found. He sliced it in 10 slices, that one annual ring, and he measured the concentration of the hemicellulose, the main components of the hemicellulose, galactans and mannans. And he could see that early in that annual ring there was less galactans, and then towards the end of the growth of the annual ring they increased. He also measured calcium along the growth of the year of the tree. And this is the result. So how to make use of this information in practice, I have no idea, but I think it's a fascinating piece of fundamental work. And with this, I want to acknowledge our collaborators and thank you very much. Thank you.
Thank you for a fine presentation, an inspiring talk, and a lot of work that has been done. with more areas for work that many people could pick up here. And we have time maybe for 1 or 2 questions. So let me see your hands if there is. Do I see anybody who wishes to ask? Here's the specialist, you know. Try to get hold of him and get his feelings. Okay, yes, please. Elaine, go to the microphone over there and state your name and affiliation.
Oh, okay. Hey, thank you. I have Elaine Oren, where am I from? University of Maryland. I had 2 questions. One is sort of one has to do with the safety of forests. I know what we were trying to do is clean up after the logging, but I always thought the debris that was out there was pretty good for the future growth. So some decisions would have to be made if you were going to collect it for biomass. That was my first question. And the second one was just a curiosity. When you showed a comparison between the model and the measurements, and the measurements showed the funny little bump at the end and then went down. Do you remember that graph? Mm-hmm. The model had the right trend, but it really didn't qualitatively show the bump at the end. It sounded like there was something totally new happening, possibly there, some acceleration process. So those were my 2 questions.
Thank you.
Thank you.
The latter one, you referred to the nitrogen oxide production curve. Okay, I first answer that. You're right, it followed the smooth trend, but then there was a little interesting dip there. And it repeated itself for most of them. That's a good point. We have been thinking about it, but we don't have a ready answer. Probably something happens to the particle at the very end of the char burnout, which some collapse or something that suddenly gives an additional little kick. But that's open. That's a good question. About the sustainability of biomass use, that's a very, very important and big issue, of course. One thing that is happening in my part of the world, in the northern Europe, I think the situation is quite good. We keep close track at the growth of the forest versus the use of the forest. And the last 5-6 years, the growth has been much higher than the annual use. So there is still an increase of the capacity. Then the other side is, of course, the nutrients and the minerals which are removed, particularly when we start using these green parts of the tree. If they are also collected previously, they were left in the woods, and that way the minerals stay mostly there. But if we start using them, then we remove them, and then it requires some minerals to be brought back. There are big programs in using the ash from these combustion systems and bring them back to the forest as a fertilizer. So that's an issue also.
Are there further questions? We can maybe take another one. Yep, please.
Yeah, Stephen Shi. Can I ask about, can you make a comment on the PM 2.5 in biomass combustion?
So, I thought he had a question over there. I'm sorry, but no. Then please let me see. Who wants to comment? I can't see you. Okay, there.
Yeah, I ask
sorry.
again about
Yes.
the PM 2.5 in biomass combustion. Could you comment on that?
Yeah. In the large scale units, which I have referred mostly to, particles are not a especially big issue because the cleaning system is good and the combustion is efficient. But most of the discussion connected with small particles and biomass use are connected with small scale units, ovens, small furnaces, where the control is not so good. And since they are many in number and the control is not good, that's a big issue, and that's a good area for improvement and research also, to have small scale firing which is efficient enough to control the PM particles.
So I think with this we should conclude this session. Let me thank Mikko again. And there may be a few housekeeping issues, but first we would like to have him open the certificate and have his photo. Thank you.
Okay. Okay. So how do we, oh, that way.
Not upside down.
Yes, okay.
Okay.
There you go.
Okay,
Thank you.
Thank you very much. Thank you.
Thank you.